Hello and welcome back. Mr. Eicher here to teach you a lesson from 9.1. These are the 9.1 notes. This is part 2 of probably a 3-part lesson. So let's consider the arithmetic sequence, -8, -6, -4. This is a term we learned about in the last lesson. An arithmetic sequence is one where you are adding a common difference d to get to the next term. So it appears that we're adding 2 plus 2. Adding 2 to get to the next term, -8 to -6, adding 2. -6, -4 is adding 2. So our next number would be -2, and then 0, and then a 2, and then a 4. So question A says, graph the first 7 terms, 1, 2, 3, 4, 5, 6, 7, so we have all 7 terms. Graph the first 7 terms. What would the graph be if you connected the dots? Well, just to review from the previous lesson, the domain are the counting numbers, the natural numbers. So the domain would be, let me color code, stylish. So this is our first number, this is our second, this is our third, this is our fourth, fifth, sixth, and seventh. So our domain would be 1, 2, 3, 4, 5, 6, 7. And then our range, color coding, our range would be -8, -6, -4, -2, 0, 2, 4. So when we're asked to graph, we're basically going to graph the ordered pairs 1, -8, 1, -8, 2, 4. I think that's right here, 1, -8. The ordered pair 2, -6, 2, -6, I think is right there, if I counted right, 2, 4, 6, yeah. And then as we continue to graph those, this type of pattern should look familiar to you. That's 5, 0, and then we got 6, 7, 6, 2, I mean, 6, 2, and then 7, 4. So there's our arithmetic sequence graphed. What type of graph would it be? It appears that it would be a linear function, a linear graph. We're not going to connect the dots though, because our range has particular values. So this is a discrete, not a continuous range. Continuous would allow us to have values kind of in between the blue dots, but the arithmetic sequence just jumps around from -8 and then jumps to -6. It doesn't have any -7, it doesn't have -7.5, so we don't actually connect the dots. Next, review the previous lesson, or the 9.0 lesson. Write a recursive formula. So recursive formula, we have to say what our starting point is, a sub 1. Our starting point is -8. And to get any term, a sub n, we would take the term before it, a sub n minus 1, and we add 2 to that term. And this is only defined for n's greater than or equal to 1. So that's our recursive formula. Our explicit formula, well, since we have this graph, we could tell what the slope is. Remember, explicit formula would just be one equation, a sub n, to get any term. How could we get any term? So we don't want to have to base it on the previous term, we just want to base it on n, where we are in the sequence. So looking at this dot plot over here, this linear looking function, this relation, there you go, that's the word, discrete relation. It looks like our slope is 2. And we'll use n. And then it looks like our y-intercept would be down there at -10. So let's see if this works. If I plug, let's see, I'll just pick one of these. If I plug 2 in, I should get 6. So if I plug 2 into this, I should get 6. What do I get? Oh, sorry. I read it backwards. If I plug 6 in, I should get 2. If I plug 6 in, I should get 2. 12 minus 10 is 2. Yeah. So that looks like this is our explicit function, and this is our recursive function. Now the explicit function is really beneficial. Even though it might be a little harder to write, the recursive formula typically is easier to write. But the explicit function is really beneficial because for the next part, on part C, use your equation to predict the 25th term. That would be difficult. To get the 25th term with the recursive function, we'd have to do this. We'd need the term before it, the 24th term plus 2. Well, I don't really know what the 24th term is. I'd have to figure out the 23rd, and then I'd have to figure out the 22nd. I'd have to keep going backwards. I don't really want to have to do that. So instead, we can use this explicit formula, and we could say, well, the 25th term would be 2 times 25 minus 10. So that's 50 minus 10. So our 25th term in the sequence is 40. So that's one use of the explicit formula, which is a little more beneficial than having to find all the particular terms. There is a way, though, that we can develop a formula for an explicit formula based on this idea of a recursive function, and that's on the next page. So let's turn over there. So on the top of the next page, we have find the pattern. So a sub 1 is the first term, a sub 1. A sub 2, recursively, we would find a sub 2 by taking a sub 1 and then plus our common difference, if this is an arithmetic sequence. A sub 3 would be the term before it. Well, we just said the term before it was a sub 1 plus d. That's the term before it. And then we'd add d to that, and that would be our third term. So simplifying, that would be the first term plus 2 differences. To find our fourth term, we would take the term before it, which we just found was a sub 1 plus 2d's, and we'd add d to that. So that would be a sub 1 plus 3d's. So let's pause and see what we have here. To get the third term, we do a sub 1 plus 2d's. To get the fourth term, we do a sub 1 plus 3d's. So if we wanted the nth term, we would do, well, a sub 1 plus how many d's? Maybe I'll write it over here so you can see the parallel here. We do a sub 1 plus how many d's? So a sub n is how many of those? Well, a sub 4 was 3 of them, a sub 3 was 2 of them, a sub 2 was 1 of them, a sub 1 was none of them, no d's up here. So it seems that we could reason that if we want a sub n, we need n minus 1 of those d's. And this formula, a sub n equals this formula is our formula for our nth term of an arithmetic sequence. So the nth term, a sub n, with the first term as a sub 1 and a common difference of 1, is given by a sub 1 plus n minus 1, that's how many, n minus 1, d's, where n is any positive integer. This will be a helpful formula to memorize and to use as we go about this chapter. So let's use this formula on these next questions 7, 8, and 9 so you can see what it looks like. So in the first one, we're asked to find a sub n, and a sub 1 is -4, d is -9, and n is 20. So we're asked to find a sub n, so a sub n equals a sub 1 is -4 plus 20 is n, 20 minus 1, times the common difference. Make sure you use parentheses here around the common difference of -9. So that would be -4 plus 19 times -9. And our answer we would get is -4 plus 19 times -9. So our nth term is -175. And actually we know what n is, a sub n. N is 20, so our 20th term is -175. So let's think about what this is telling us. If we start at -4 and we have a common difference of -9, so let's go here. If we start at -4, -4, I need a -4, there we go. If we start at -4 and we're adding -9 each time, that means our second term, our third term, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 19, 20. So that means our 20th term would be -175, and that's what we just found. So how many times did we add a -9? Well, down here, not sure if you could see that, but down here at the very bottom it says enter in a purple 19. There it is. 19 times we added -9. And that's what this formula does. 19 times we added a -9. So it's a pretty cool formula. Let's look at another example. We're looking for find a sub 12 for this sequence. Now it could very well have like a ... but at least this sequence shows us what the a sub 1 is. A sub 1 is the first term, so the first term is 8, plus n minus 1, we'll talk about in a second, times d. The common difference, we could see the common difference is we're subtracting 5 each time. So the common difference is -5. And then n, if we want the 12th term, we have to use 12 as our n minus 1. So this would be 8 plus 11 times -5. That's 8 plus -55. And what is that? -47. So our 12th term is -47. Using my calculator, if we start at 8 and we're adding -5 each time, 8 and we're adding -5 each time, so we start at 8 and we're adding 5 each time, and we're going to 12, so that would be 1, 2, 3, adding -5. So we're starting at 8 and we're adding -5 each time, and we're going to 12 terms. So my second, my third, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So the 12th term is -47. Is that what we got? 12th term is -47. Oh, I erased my work. Well, I hope so. I'd encourage you to pause this video and see if you could do number 9 next, and I'll come back with the answer momentarily. So number 9, we're looking for a sub 25. That also tells us n is 25. The common difference, it looks like we're subtracting 2 each time. And then a sub 1 is the first term, negative 3. So plugging these in, we'd have a sub 25. The 25th term is the first term plus n minus 1, which really you could just put 24 there, times a common difference of negative 2. So we'd have negative 3 plus, we need 24 of those negative 2's that we're adding. So negative 3 minus 48, it looks like our 25th term would be negative 51. So if we're starting at negative 3 and we're subtracting 2 each time, so we're starting at, I forgot already, starting at negative 3 and subtracting 2. So we're starting at negative 3 and we're adding a negative 2 each time. And we're going until the 25th term. So that's my second term's negative 5. And we got negative 5, second term, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5. So our 25th term is negative 51 in this arithmetic sequence. And negative 51 is, oh, I just lost my work. One of these days I'll get the hang of this. But I think we said negative 51. So thank you for watching this video. The last part, we'll be talking about a new sequence called a geometric sequence.